So we were on continuous growth with population. We have our continuous growth formula again on an exam. That formula would be given to you and each of the letters would be explained except for the letter E because it's not a letter. It's a number, right? This is where if kindergarten kids were in here right now, they'd be like, I can't go to school anymore. In grade 12, they tell you that E is a number. So what's happening? Educational system must be destroyed.
Or when you say like square root of -1 equals I.
Yeah, E is a number, but I is just an imaginary number. E is a real number, I is an imaginary number. They're like, all right, I just give up. So the question is, when will the population reach 6 million? So we plug everything in, and I wrote things here, instead of writing 6 with all the zeros, and 1,1,380,000 with all the zeros, I just already wrote it in millions. I basically divided both sides by a million so I didn't have to write as many numbers. Are you okay with that? If not, you could definitely write 6 million and 1.38 million. Now, because there is an E in here, when we're solving for an exponent, we take the log of both sides, but I would suggest taking the natural log of both sides. Also, we're going to find the strategy of if you can simplify to get the power by itself first, it will make your log laws easier. So I divided both sides by the 1.38. That got my power all by itself. And it's going to make my log laws a little bit easier. If I had taken the log or natural log right at the beginning, you might be tempted to bring the exponent out, but you can't because it's an exponent just to the E. See how this exponent in the green box doesn't touch the 1.38? So you have to do an extra log off of that. And now I can take the natural log of both sides. That exponent can come out in front. And the reason that natural log is nice is because the natural log of E is equal to 1. So if you have natural log of E all by itself, it can just go away. It doesn't have to though. So I can have it just go away because it's equal to 1. Or here, I wrote it in green. If you had divided also by the natural log of E, it would not be wrong. So as far as cities go, if Vancouver probably right now has a population model. And they use that model to look forward, what's the population going to be like in 5 years? And what's that going to mean for our roads? What's that going to mean for our electricity? How do we have to prepare so we're ready for it? So these population models are used all over the world to try to predict the future and use it to help them figure out what kind of infrastructure they're going to need.
When did you do this example?
Hmm?
When did you do this example? In 1985?
Well, if you look at the beginning, it says in 2011, the population, no, here, in 1981, it was 1.38. So 1981 was our starting point. If we added 86.5 to 1981, that's how we would figure out that 2067.
2006,
0.45. Okay.
Oh, I swear the population of Vancouver was very small.
Depends what they count as Vancouver. Like, do they count Vancouver as Greater Vancouver area or just City of Vancouver? These are the hardest questions that you will get. Well, one of the harder. There's some hard ones too. There's a couple of hard ones to get. This is one of the harder questions that you will get. Population of a herd of gophers was first studied was 15,000. 6 years later, the population is 18,000. How long will it take to triple? Okay. This is what makes this question a little bit difficult. You want to find t, because it says how long will it take to triple. But when I look at the formula, I want it to triple, so I have an original amount. I can take the 15,000 or the 18,000. I can triple it to get the amount. But I don't know t because I want to solve for that. I also don't know what r is. It doesn't tell me anywhere in the question at what rate the population is growing. So there's two things in the formula I don't know. I don't know r and I don't know t. When there's two things that you don't know, you have to find one of them first. And if the question says find t, most likely you can't find t first. You're going to have to find r first. Is there enough information in here that we can put things into that formula so the only thing we don't know is r? Well, we knew it was initially 15,000 in 6 years, so that would give us a t value. It's 18,000, so we can go 18,000 equals 15,000 e to the r, and it's in 6 years. Again, here is my power. If you can get that power by itself, your life with logarithms is a little bit easier. Can you see that you could divide both sides by 15,000? That'll just give me 18 over 15. I could reduce that further if I wanted to, but I don't need to. Now I can take the natural log of both sides. And since it's a single power, that exponent can come out in front. Natural log of e is 1, so it could just go away. I can divide both sides by 6, and I can find out with what r is. And notice here that I did a couple decimal places, and then I went dot, dot, dot. I am not going to round early. Rounding early might cause my final answer to go bad, which could be a problem. So I want to make sure that I keep all the decimal places for this for my calculations later on. In some calculators, you can store that answer as A, or store it as B, or store it as C. If you have your scientific calculator already, you should check. How do I use my calculator's memory to store a value? Because it can be really helpful. Now that we found R, now we can figure out how long it takes to triple. Because I know a starting point, it's going to triple to get an amount. Now the number one question I get on tests is like, what should I use? Should I use the 15,000 to triple or the 18,000 to triple? What did we learn the other day? It doesn't matter, right? When we learned that it took the same amount of time for $30 to double to 60, that it would take $1 million to double to 2 million, same thing with tripling. It's going to take the same amount of time to triple, whether you started with a little amount or a big amount. So you can choose either one, because if you tripled it and then simplified, you see that you get a 3? Whether you tripled with the 18,000 or the 15,000. And in here I write my R value to find T, but I put the decimals there to say I'm not rounding early. Here's my power. Is it easy to get my power by itself? Yes. Divide to get that 3. My power is by itself. Now I can take the natural log of both sides. Natural log of E is 1. And again, now I have, so this is where you would be typing things into your calculator again. And you had this as your last answer, so you could just go natural log of 3 divided by your answer. And then you're not rounding early. I should have 3 decimal places here. And this question has units, so you have to have units as well.
Can you just explain natural laws? Like, is the base of a natural log E?
Yeah.
So it's like,
So this is
what
what,
makes it the natural log? Like, why is that one chosen to be natural?
because the number e is super important.
So log E.
Log e of e is the same as the natural log of e. Wow.
But then what is just the ln by itself?
ln is like log e. This part here, ln, means the same as this.
Okay.
Log base e.
And why is E important? Like, what does it do for us?
So
Like, I is
in calculus, it is the only number whose derivative of its exponential function is exactly the same. E is important because it shows up in continuous growth formulas, which we didn't derive, but it shows up in continuous growth formulas. It comes from a crazy pattern. Check this out. Let's see what happens when we do this. Can you type this? Let's type this all. Let's do it together. Okay. I'm gonna put brackets here. 1 plus, and I'm going to use here. Clear. What? I'm gonna actually do it here. I'm gonna type it into my graph. I'm gonna go 1 plus 1 divided by x, bracket to the power of x. And I'm gonna go to my table of values so you can see, we got some errors here. Whoa. Okay. Check it out. Error when you get one. But if you plug in 1 for this equation, 1 plus, I'll write it over here so we can see it as we're going along. If you plug in 1, do you see that 1 over 1 would be 2? 2 to the power of 1 is 2. Okay? I plug in 2, I get 1 plus 1 half, which is 1.5. 1.5 squared happens to be 2.25. The crazy thing about this formula is in your mind, if x was really, really, really big, like 1,000,000, what does 1 over a really, really big number get close to? 0. So in my mind, if x was super, super huge, I would think this should be 1 plus 0 to a super huge exponent. And 1 plus 0 is 1. And 1 to any exponent should be 1. But it actually doesn't work that way. As x gets bigger and bigger, check out the numbers as I go through the bigger and bigger numbers. 2.6, 2. Does it seem like it's not going up very fast?
Yeah.
Okay. In fact, if I here, I'm gonna graph this. Oops, I'm gonna just hit the graph button. There's the graph of this. I'm going to go from a small number. I'm gonna go super big number. Can I graph on this? Huh. As it gets super big, it looks like it's straightening out. It looks like it has a limit. It's going to a certain value. In fact, from here, I can calculate any numbers that I want. Like, what is its value when it's 50? 2.69. What about when it's 100? 2.70. What about 500? 2.715. What about 11,000? 2.718. Is this looking like anything? If I did 100,000, 2.71826. If I keep going higher and higher, it's going to get closer to 2.718281828, and then keep on going. It's going to get closer and closer to E. Okay? Check this out. In our compound interest formula, you see that we had 1 plus the rate over compounding periods to the power of the compounding periods. So our compound interest formula naturally had this built in, and that's why the continuous formula gets the number e. So the number e naturally appears in real life, representing continuous growth. In calculus, sorry, getting a little bit off topic here. For some of you, when you study calculus next year, here is the graph of e to the x. It has the point 0, 1. It has the point 1, e. And the first bit of calculus that you're going to learn is all about slopes of tangent lines. What is a tangent line? A tangent line is if I pick this point right here and I draw a straight line that touches just that point on the graph. Calculus is about figuring out what's the slope of this tangent line. And for the e to the x, at that point, it happens to be 1. For e to the x, at this point, it's got a steeper slope. Its slope happens to be e. In fact, it is the only graph that exists in mathematics where no matter which point you pick, so if I pick some point up here, x, y, and I drew its tangent line, the slope of that tangent line is always going to be y. Always exactly what you started with. So one of the things you'll do in calculus is you'll draw graphs, and you'll graph their derivatives. The derivative graph of e to the x is exactly the same as its original graph, and it's the only number that does that. So it's important in calculus that way. That's why after this year, you don't use logarithms, because calculus works out so beautifully if you use e. But all the other numbers, it's a little bit off. Pi, your first super important weird number that you learned, okay? Pi is a relationship between a diameter or a radius and its circumference. And then it shows up all over everywhere else. E is another such special number. These numbers are called transcendental numbers. And a crazy thing in mathematics is they've actually, this is where there's crazy things in math. When you work with infinity, infinities are weird. There's an infinite amount of fractions. There's an infinite amount of whole numbers. Mathematically, they've shown that those infinities are the same size. There's the same amount of fractions as there is whole numbers. Even though you can find a fraction that's not a whole number, and even though every whole number is also a fraction, you would think that there would be more fractions than there are whole numbers, but no, at infinities we say they're the same size. Okay? If you include all rational numbers that are fractions and compare them against all irrational numbers, they have proven that there is actually infinitely more as far as infinities go. There's different levels of infinities. Irrational numbers happen more often than rational numbers. Yes.
How do you prove anything with infinity? At
Well,
all?
The first mathematician who went into this, you feel sorry for him. There's actually great books written about him. His last name, his whole name was Georg Cantor. He studied infinities. He's the first one to say there's different levels of infinities. Okay? Throughout his whole career, everybody else in the mathematics world at that time, this is early 1900s, I think. Don't get my history might be off by give or take 50 years. Everybody during his lifetime said, your mathematics is stupid, you're insane. Your mathematics is stupid, you're insane. Okay? He went insane because people told him he's insane the whole time. He died thinking nobody thought his math made any sense. And only 30 or 40 years later, they said his discoveries in infinity have advanced mathematics beyond what we thought was possible because of that. So some of the applications of this is if I would take this ruler stick and I had a super sharp samurai sword, and I would go whoosh, and I'd cut it. It would cut somewhere between 0 and 100 centimeters. It would either cut it at two perfectly like it's possible that it could cut perfectly at 20 centimeters, right? And then I have two rational numbers, 20 and 80, or 20.5 and 79.5. But mathematics has shown since there's infinitely more irrational numbers, if you randomly cut this somewhere, you will actually randomly cut it at an irrational number and not an irrational number. Every single time, actually. If you randomly cut it, I think it's impossible to cut it at, I don't know. This is where infinities get, that your brain goes a little bit mush. So he proved that there are infinitely more irrational numbers than rational numbers. So if we make it fair, a bunch of irrational numbers are square roots, cube roots. Cube root of 3, irrational. We're like, let's put all of the radical numbers that are irrational. In fact, let's put all of the numbers that can be solved. If you solve any polynomial equation, we'll call those algebraic numbers. Since the teams are unfair, the rational numbers are losing all the time, we'll give you guys all of these numbers. We'll give you all the algebraic numbers. And all that's left on the other side are the transcendental numbers. Pi and e. And pi squared and e cubed and like those ones. And there's still infinitely many more of those than there are of rational numbers and algebraic square roots. And what's crazy though is we know in our world about pi, and we know about e, and we know a couple of more. You can look them up. It's like I think under 20 that our world has discovered of super important transcendental numbers that explain world effects. And yet there's infinitely more of these than all the other numbers, and we've only discovered a few of them. And it has taken like proving that pi was transcendental took like hundreds and hundreds of years. Yes.
What's your favorite? Is there like a really cool number? Like
Well,
one that
pi
we
and
know
e.
about?
I think there's like a gamma in there. I'm not sure what but I don't use those ones. I'll see if I can find a list for you by the end of the class. But there are these numbers that go on forever without a pattern, and yet show up in our universe, in our mathematics, and what we do. Like mathematicians, when they discovered pi as like the relationship between circumference and radius, no matter how big or how small the circle, and then that pi also showed up in the area of the circle, in the volume of a sphere, and it's like, what the heck? And it doesn't just show up in geometry. Pi has since then shown up in other things. And it's like, why is this number special? Why is E special? What other, like, is there in the next 500 years, are they going to discover a new super important number that we don't know about yet? There's infinite amount of these numbers, but we've only discovered a couple of them. Oh, crazy. Okay. Now, going back to the question we just did, I made a grammatical error, an English grammar error, or an English, I don't know if it's grammar. There's something wrong in my English in this question. And it's hard to pick out, but maybe someone can find it. There might be more than one thing wrong with my English. So you might, but there's one in particular that I want to know if you can figure out.
Is it a herd of gophers?
It is not a herd of gophers. English is crazy. For some reason, we have decided in English that every group of animals should have its own weird special name. You know some of these, like what do you call a group of fish? A school. You're in school. Are you guys fish? No.
The murder of crows.
Murder of
Say that.
crows.
Just have to say that.
Have you heard of that? If you have a bunch of crows, we say, oh, there's a murder of crows. Someone gaggle of geese. Like we have some that we use more often. Gophers, technically. Does anyone know the technical group of gophers? It is a colony.
That makes sense.
Colony of gophers. Makes sense, right? Just like, oh, schoolfish, makes sense. Right?
Totally makes sense.
Conspiracy of lemurs.
A
Oh yeah,
conspiracy!
conspiracy. That's my favorite one. That's my favorite one.
Conspiracy of lemurs. I feel like there's a lot of lemurs going on, right?
That was the conspiracy.
That's like, yeah, there's something going on there.
Caterpillars.
What's the group name for people?
We're a group of people, we're so boring.
That makes
Is it
sense.
just group actually?
I don't know, I don't know.
Parliament of owls. Why does it
Parliament?
have like conspiracy and murder of my
Government
favorite?
system.
Here is my last question. This is actually true. You do call a group of rhinos a crash.
That's funny.
A crash of rhinos. I want you to try this one on your own. I guess they run into you, so that would crash.